There is a star in the night sky that has been dying for longer than our species has existed. You can find it without a telescope. On a clear winter night, look for Orion, the hunter, the warrior, the outline of a giant, standing against the dark. Find the three stars that form his belt and then look up and to the left. There it is, a point of reddish-orange light, slightly smouldering, like an ember that hasn't quite gone cold. It's brighter than almost anything else up there. It's been burning since before the first human beings looked up and wondered what fire in the sky could possibly mean. That star is Betelgeuse. And for most of human history, we assumed it would keep burning more or less forever, or at least for longer than any time scale that could mean anything to us. Even when astronomers began to understand stellar evolution, when they mapped the life cycle of stars and traced the long arc from gas cloud to nuclear furnace to eventual collapse, Betelgeuse seemed far enough along that its death was a matter for the distant future. A theoretical concern. A footnote. The number that kept appearing in papers, in textbooks, in science articles and YouTube explainers was this. Betelgeuse has roughly 100,000 years left. Some sources said 10,000, some said 1,000,000. The range was wide because the uncertainty was enormous, but the underlying message was always the same. It will explode, yes, but not soon. Not in any time frame that a human being should think about with anything other than academic interest. That comfortable estimate is now under direct challenge. In 2019, something happened that nobody fully expected. Betelgeuse dimmed, not slightly. Not within the normal range of its well-documented fluctuations. It dimmed dramatically, enough that it became one of the most discussed astronomical events of the year, enough that the phrase, "Is Betelgeuse about to explode?" started trending on the internet, enough that astrophysicists around the world turned their instruments toward it with a sense of urgency that peer-reviewed science rarely permits itself to express openly. It did not explode. The dimming had an explanation, a messy, chaotic, almost violent explanation involving a massive surface eruption, a cold, dark cloud of ejected material, and a star that was visibly struggling to maintain the equilibrium that had defined its existence for hundreds of thousands of years. But what came after that explanation was, in some ways, more unsettling than the dimming itself. Because when scientists went back through the data, not just the 2019 event, but years and decades of observations, they found things that didn't line up with the older models. Patterns that suggested a star not centuries away from its final act, but one that might be in the late stages of the process that leads directly to detonation. Pulsation cycles that had changed, a surface that was heaving and contracting in rhythms consistent with the very last phases of stellar life. Chemical signatures pointing to a nuclear burning sequence that the older estimates had assumed was still far in the future. And then, in 2023 and 2024, new data from multiple observatories, including instruments with capabilities that simply didn't exist 10 years ago, began to sharpen that picture further. Papers started appearing with titles that would have seemed alarmist a decade ago. The phrase "imminent" on astronomical timescales began to carry a different weight, and the number that some researchers started cautiously putting into their models was not 100,000 years. It was closer to a few hundred, perhaps less. Now, before we go further and before the inevitable question arises, let's be precise about what imminent on astronomical timescales actually means, because this is where popular science coverage often either overstates or misrepresents what the researchers are actually saying. We are not talking about next Tuesday. We are not talking about your lifetime or your children's lifetimes, or even, with high confidence, the lifetimes of the next several generations. The revised estimates we're discussing place the probable detonation windows somewhere in the next few hundred to perhaps a couple thousand years. A handful of models push that number lower. None of the serious peer-reviewed work suggests it's going to happen tonight. But here is the thing that matters. The difference between 100,000 years and a few hundred years is not a minor correction. It is not a rounding error. It is a revision so substantial that it changes the entire category of the question. When the timeline was 100,000 years, the death of Betelgeuse was cosmological background noise, something to note, to study, but not to feel. When the timeline is measured in centuries, it becomes something else. It becomes, for the first time, a stellar event that might be witnessed. Not by us, but by people who will live in houses and walk on the same ground and look up at the same sky we do. That is a different kind of knowing, and it deserves a different kind of attention. This video is going to walk you through the full picture, not just what Betelgeuse is and where it sits in its life cycle, but what specifically has changed in the data. What the 2019 dimming revealed about the star's interior that older instruments couldn't see, what the updated models are saying about its timeline, and what it actually means, in practical and profound terms, for a star of this size and this proximity to explode. Because Betelgeuse is not just any star, it is one of the largest objects in the observable universe. If you placed it at the center of our solar system, where the Sun sits right now, its surface would extend past the orbit of Jupiter. In some models, past Saturn. It would swallow every planet that human beings have ever visited, every probe we have ever launched, every place in the solar system that we have ever pointed a telescope and seen up close. All of it inside the star. When something that size explodes, it does not go quietly. A supernova is among the most violent events the universe is capable of producing. For a brief period, days to weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of suns. The energy released in those first seconds exceeds what our Sun will produce across its entire 10 billion-year lifetime. A wave of neutrinos punches outward at nearly the speed of light, yet the outer layers of the star are hurled into space at 10% the speed of light. A shockwave tears through everything the star has built up over its long life and flings it into the void as raw, elemental material, the ingredients for future planets, future stars, future life, and Betelgeuse is 700 light-years away. That is far. In the context of the galaxy, it is not particularly close. There are hundreds of stars closer to us than Betelgeuse, but in the context of supernova danger, 700 light-years is close enough that astronomers have done the calculations carefully, and those calculations have consistently found that when Betelgeuse goes, Earth will be in no danger of catastrophic harm. At the lethal radius for a supernova, the distance within which the radiation and particle flux could strip the ozone layer or cause mass extinction is generally estimated at around 25 to 50 light-years. Betelgeuse at 700 light-years sits comfortably outside that range. What Earth will experience is something altogether different from danger. Something, in fact, that might be described as one of the most spectacular astronomical events the human species has ever witnessed, assuming any humans are around to watch it. When Betelgeuse detonates, it will become visible in daylight. For weeks, possibly months, it will shine bright enough to cast shadows at night. It will be the second brightest object in the sky after the sun. The night sky will have effectively two suns, one that sets and one that doesn't. Depending on the exact timing and the geometry of the explosion, it may be bright enough to read by at midnight. Civilizations that encounter it will have no precedent for it. History will divide into before and after. Now, hold that image. A sky with two suns, a star bright enough to read by, a light that has travelled 700 years to reach you. Hold it, and then consider. Someone in the year 2200 or 2400 or 2600 might actually see it, might go outside, look up and watch a star die, or it might be us. The revised timeline is uncertain enough that no one can rule it out entirely. The lower bound of some of the new models is measured not in centuries but in decades. Those models are not the consensus. They represent the more aggressive interpretations of the data. But they exist. They've been published. They haven't been refuted. To understand why the timeline has been revised so dramatically, you need to understand what Betelgeuse actually is and what phase of life it's in. Not in the simplified version that most science journalism provides, but in the real, messy, extraordinary detail of a star that is doing things that even veteran astrophysicists find genuinely surprising. Betelgeuse is what astronomers call a red supergiant. The word giant is almost comically inadequate for what it describes. The Sun has a radius of about 695,000 kilometers. Betelgeuse has a radius somewhere between 700 and 1,000 times that. The measurements vary because Betelgeuse itself varies, expanding and contracting in long pulsation cycles that make it difficult to pin down an exact size at any given moment. While the best current estimates put it at roughly 900 to 1,000 solar radii on average. That means if Betelgeuse and the Sun were side by side, you could fit approximately 750 million suns inside Betelgeuse by volume. It is a number that does not resolve into intuition no matter how many times you say it. It is also, and this is crucial, not a star in its prime. It was once. At the beginning of its life, some 8 to 10 million years ago, Betelgeuse was a hot, blue, main sequence star burning hydrogen in its core through nuclear fusion, the same process that powers our Sun. It was massive, perhaps 15 to 20 times the mass of the Sun at birth, though it has lost significant mass over its lifetime through powerful stellar winds. For millions of years, it burned steadily, a reliable, if unremarkable furnace. Then the hydrogen ran out. When a star as massive as Betelgeuse exhausts the hydrogen in its core, it undergoes a transformation that is, in stellar terms, catastrophic and rapid. Without the outward pressure of hydrogen fusion to balance gravity, the core contracts. That contraction heats the core to temperatures sufficient to fuse helium, the ash of hydrogen burning. The star's outer layers respond to the changed energy output by expanding enormously, cooling as they do so, shifting the star's color from blue-white to orange-red. This is the transition from main sequence to red giant, or, for very massive stars, red supergiant. This expansion is not gentle. The outer atmosphere of a red supergiant is so loosely bound that it is technically part of the star in name only. Not the gas that makes up those outer layers, the layers you're seeing when you look at Betelgeuse in the night sky, is barely denser than a laboratory vacuum. If you could somehow stand inside Betelgeuse's outer atmosphere, you would feel almost nothing. The density is lower than the air at the top of Mount Everest, lower than many of the vacuums scientists create in their labs, but it extends across an almost incomprehensible volume, and it glows, and it pulses, and right now it is doing things that are telling scientists something important about the clock ticking inside. Because here is where we get to the heart of the revised timeline, and here is where the story of Betelgeuse becomes genuinely new rather than merely reviewed. A massive star like Betelgeuse does not burn just one element. After the hydrogen is exhausted, helium burning begins. After helium is exhausted, carbon burning begins. After carbon, neon, then oxygen, then silicon. Each successive burning stage produces heavier elements as fuel and heavier elements as ash. Each stage is hotter, more intense, and, crucially, dramatically shorter in duration. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands. Carbon burning lasts perhaps 1,000 years. Neon burning about a year. Oxygen burning months. Silicon burning days. That final stage, silicon burning, which produces iron in the core, is the detonator. Iron cannot be fused to release energy. Instead, fusing iron requires energy. When silicon burning concludes and the core becomes iron, there is no longer any fusion process capable of holding up against gravity. The core collapses in less than a second. The outer layers, suddenly unsupported, fall inward and then rebound in a shock wave that tears the star apart. This is the supernova. The critical question, the question that the new data is trying to answer, is which burning stage is Betelgeuse in right now? The older models, the ones that generated the 100,000-year estimates, were built on assumptions about Betelgeuse's interior that were largely inferred from its surface behavior and its position in stellar evolution models. Those models placed Betelgeuse in the helium-burning phase, perhaps just beginning to transition toward carbon burning. If that's where it actually is, the remaining timeline is indeed tens of thousands of years at minimum. But some of the newer work suggests something different. At the pulsation patterns of Betelgeuse, the way it swells and contracts on timescales of hundreds of days, have been studied in increasing detail, and those patterns are sensitive to conditions deep inside the star. A star in helium burning pulses differently from a star in carbon burning. The modes of oscillation carry information about the composition and temperature of the interior, even when the interior is hidden from direct observation by hundreds of solar radii of hot gas. And what the pulsation data suggests in some analyses is that Betelgeuse may already be in or approaching the carbon-burning phase. If that interpretation is correct, and it is contested, we'll address the debate honestly. Then the timeline is not 100,000 years. It is not even 10,000 years. It is hundreds of years, possibly less. Possibly within a few human generations. That is the revision. That is the number that changes everything. But to understand why scientists believe it, and to understand why other scientists push back, you need to understand what happened in 2019. Because the great dimming of Betelgeuse, the event that first drew mass attention to this star's instability, was not just a dramatic moment for public science communication, it was a diagnostic event. It revealed things about Betelgeuse's interior and behavior that had never been observed before, and it opened lines of inquiry that are still producing new results today. In the months between October 2019 and February 2020, Betelgeuse lost about 60% of its visual brightness. It went from being one of the brightest stars in the sky to something noticeably dimmer, not just to instruments, but to the naked eye. People noticed. Amateur astronomers noticed. Anyone who had looked at Orion for years noticed that something was wrong. The dimming was so extreme that astronomers immediately began publishing papers trying to explain it. The initial hypothesis that generated the most public excitement was the one that fit the narrative perfectly. Maybe Betelgeuse was about to explode. The dimming, in this interpretation, was a pre-supernova event, the star beginning its final convulsions. It wasn't. Or at least, if it was a much earlier warning signal than anyone anticipated. What the follow-up observations revealed was that Betelgeuse had experienced a massive surface mass ejection, a process somewhat analogous to the solar flares and coronal mass ejections our own Sun produces, but on a scale that makes the Sun's version look trivial. A bubble of superheated plasma the size of several planets had risen to the star's surface, burst, and ejected an enormous cloud of material outward. That cloud of material, cooling as it expanded, condensed into dust, dark dust, which blocked the light from the star's surface and caused the dramatic dimming. This was, in itself, extraordinary. The event was the largest stellar surface mass ejection ever directly observed. It was violent enough that it left a visible scar on Betelgeuse's surface, a cooled, disrupted region that persisted for months afterward. The star, in a very literal sense, had blown off part of itself. But here is where the story gets more complex and more interesting than the surface-level explanation suggests. After the dust cloud dispersed and the surface brightened again, astronomers noticed something else. Betelgeuse's normal pulsation cycle, the long heartbeat that had defined its behavior for as long as humans had been carefully tracking it, had been disrupted. The rhythm had changed. The star that emerged from the great dimming was not quite the same star that had gone into it, and that change in rhythm, that altered pulsation, is one of the primary inputs feeding the revised timeline models. Because when you alter the pulsation of a star this dramatically, when the energy output of its surface mass ejection is large enough to measurably reset its oscillation modes, you're seeing evidence of something happening in the interior that is far more energetic than normal stellar breathing. You're seeing a star that is releasing energy in quantities consistent with a more advanced nuclear burning stage than the models had assumed. The data from that event has been analyzed from dozens of angles in the years since, and the conclusions that keep emerging from that analysis are not comforting if you prefer your catastrophic stellar events to remain safely in the far future. We'll walk through all of it, the full picture of what the new data shows, what the competing interpretations mean, and what it would actually look like and feel like on Earth when that moment finally arrives. But first, we need to give Betelgeuse the context it deserves, because it is not just a star that happens to be near us, it is a star that is, by any reasonable measure, among the most important single objects in the current night sky. A star that has been part of every human culture that ever looked up at Orion and tried to make sense of the dark, a star that is, in the truest sense of the word, dying, and has been dying for longer than our civilization has existed. Understanding what it is, what it has been, and what it is becoming is not just scientific literacy. It is, in a strange and quiet way, a form of keeping vigil, because whatever the final number turns out to be, 100 years, 1,000 years, 10,000 years, Betelgeuse is ending. The light we're looking at tonight is being produced by nuclear fires that are running out of fuel in a sequence that can only end one way. The star that the ancient Egyptians saw, that the Greeks wove into their myths, that the first humans who ever told stories around fires looked up and named, that star is in its last chapter. And the question the new data raises is simply this: how many pages are left? That question is not academic anymore. It is not safely theoretical. The range of serious scientific estimates now includes a window in which the answer might be not many. Not many at all. We're going to count them down to understand why the revised timeline is being taken seriously by researchers who are not, by professional temperament, inclined toward dramatic conclusions. You need to understand how stellar timelines are estimated in the first place, because the story of how we arrived at 100,000 years and how we are now being pushed away from it is itself a story about the limits of inference, the danger of overconfidence in models, and what happens when a star starts behaving in ways that the models didn't predict. Stars do not come with labels. They do not broadcast their age or their internal composition in any direct way. What we receive from them is light, a spectrum of radiation that carries encoded information about the temperature and chemical composition of their outer layers. From that light, and from the laws of physics, astronomers build models of what the interior must look like. They calculate how long certain fusion processes should take at certain temperatures and pressures. They compare those calculations to what we see on the surface, and from the comparison they derive an estimate of where, in its life cycle, a star currently sits. For most stars, this process works remarkably well. The physics of stellar evolution is one of the genuine triumphs of 20th century science. We can look at a star, measure its luminosity and temperature, and plot it on what's called the Hertzsprung-Russell diagram, and in most cases place it within its life cycle with confidence. We can look at a cluster of stars that all formed at the same time and read their collective age from the pattern of how they've evolved. But Betelgeuse presents a specific set of challenges that make this process harder than usual. And those challenges are directly relevant to why the timeline estimates have such wide error bars, and why the newer analyses are able to make a case for significant revision. The first challenge is mass. The rate at which a star evolves, how quickly it burns through each fuel stage, is determined primarily by its mass. More massive stars burn hotter and faster, but Betelgeuse has been losing mass throughout its life. We're through stellar winds so powerful that they have blasted a significant fraction of its original material into the surrounding space. Those winds create a vast nebula of gas around the star that we can observe, and from that nebula we can estimate how much mass has been lost. But the estimates vary. Some analyses suggest Betelgeuse began with a mass around 15 times the Sun and has shed several solar masses worth of material. Others push the initial mass higher. And because the entire timeline of stellar evolution scales with mass, uncertainty in the initial mass translates directly into uncertainty in the timeline. The second challenge is pulsation. Betelgeuse is what's called a semi-regular variable star, meaning it doesn't just shine steadily, it pulses, brightening and dimming over multiple overlapping timescales. The dominant pulsation cycle is roughly 400 days, just over a year, during which Betelgeuse expands and contracts as pressure waves move through its outer layers. But there are other cycles layered on top of that, a roughly 200-day cycle, a roughly 2,000-day long-period variation, and possibly others. These pulsations make it difficult to get a stable baseline reading of the star's true luminosity and size, because those quantities are constantly changing. Measuring Betelgeuse is a bit like trying to measure the height of someone who is perpetually bouncing on a trampoline. The third challenge, and this is the one that has become most scientifically significant in light of the 2019 event, is that Betelgeuse is a convective star in a way that most stars are not, at least not to this degree. The outer layers of Betelgeuse are dominated by enormous convective cells, giant bubbles of hot plasma that rise from the interior, release their energy at the surface, cool, and sink back down. These convective cells are so large that individual ones have been directly imaged. Some are a substantial fraction of the star's total diameter. They churn the outer layers of the star constantly, creating a surface that is not smooth and uniform, but irregular, lumpy, asymmetric, and in constant churning motion. This convection is not merely a surface phenomenon, it is a symptom of the energy transport process happening throughout the star's outer envelope, and the character of that convection. How vigorous it is, how deep it extends, how the cells are distributed, carries information about conditions deeper inside. Changes in the convective pattern can signal changes in the internal energy budget of the star, and in the years since 2019, the convective pattern of Betelgeuse has demonstrably changed. But let's start with the pulsation data, because that is where the clearest and most quantifiable evidence for the revised timeline comes from. For decades, astronomers have carefully tracked Betelgeuse's brightness over time, building up a data set of its pulsation history that now extends back more than a century in useful form, with rougher estimates going back further. From this data set, researchers have identified the multiple overlapping cycles and worked to separate them, to decompose the complex observed brightness variations into their component frequencies, each associated with a different physical oscillation mode of the star. The significance of this decomposition is that different oscillation modes probe different regions of the stellar interior. Some modes are primarily sensitive to conditions near the surface, others, the so-called gravity modes, which involve the bulk of the star oscillating under the restoring force of buoyancy, are sensitive to the deep interior, to the layers close to the nuclear burning core. If the composition or temperature of those deep layers changes, as they would if the star transitions from one fuel source to another, the frequencies of those gravity modes change in predictable ways. What the long-term pulsation record shows, and what has been analysed in increasing detail in papers published from 2020 onward, is that the dominant pulsation period of Betelgeuse has been shifting. The roughly 400-day cycle has been changing. And the nature of that change, the direction and rate of the shift, is consistent with models of a star that is in a more advanced evolutionary state than previously assumed. A research team led by Hideyuki Sayo, published in 2023, analyzed Betelgeuse's pulsation behavior in detail and concluded that the star's long secondary period, the roughly 2,000-day variation that sits on top of the shorter cycles, is consistent with what's expected from a red supergiant undergoing carbon burning in its core. Their analysis placed Betelgeuse in what stellar physics calls the carbon burning phase, which is separated from the final collapse not by tens of thousands of years, but by a much shorter interval. That paper was not ignored. It generated significant discussion in the astronomical community. Some researchers accepted its conclusions with varying degrees of confidence. Others raised methodological objections, questioning whether the pulsation model used was sufficiently constrained to make this claim, pointing out that alternative interpretations of the same data remained viable. The debate is ongoing, and it would be dishonest to present the carbon-burning interpretation as the settled consensus. But here is what is important about that debate. The objections raised against the Sayo interpretation have not been that the data is wrong or that the analysis was badly done. They have been largely about the degree of certainty that can be extracted from this particular type of analysis. That's a meaningful distinction. No one is saying Betelgeuse is clearly still in helium burning and the new data is irrelevant. The argument is about confidence levels and model assumptions, not about whether the revised timeline is physically possible or even plausible. And alongside the pulsation data, there is other evidence that points in the same direction. One of the most striking new contributions came from neutrino observations, or more precisely, from the implications of what neutrino detectors have and haven't seen. Neutrinos are produced copiously in nuclear fusion processes, and the type and flux of neutrinos emitted depends on which fusion process is occurring. Carbon burning, neon burning, and oxygen burning produce neutrino fluxes far in excess of what hydrogen or helium burning generates. If Betelgeuse were in one of these advanced burning stages, modern neutrino detectors should in principle be capable of detecting the signal, not from individual neutrinos, which would still be extremely rare, but from a statistical excess of background neutrino detections in the direction of Betelgeuse. No definitive signal has been confirmed, but the absence of a confirmed signal is not the same as evidence against advanced burning. The neutrino flux from carbon burning in Betelgeuse at 700 light-years would be extraordinarily faint by the time it reached Earth. The current generation of detectors sits near the edge of what would be required to make a confident detection. The upcoming Hyper Kamiokande detector in Japan, scheduled for operation in the mid-2020s, will be substantially more sensitive. If Betelgeuse is in an advanced burning stage, Hyper Kamiokande may be able to tell us definitively, and it may do so within years, not decades. That prospect, that we could receive actual empirical confirmation of Betelgeuse's burning stage within the lifetimes of people currently alive, is itself a remarkable development in the story of this star. Now, let's go back to 2019 because the full implications of the Great Dimming have still not been entirely extracted, and several of those implications bear directly on the question of timeline. The surface mass ejection that caused the Great Dimming was, as mentioned earlier, the largest stellar surface mass ejection ever directly observed. But what made it particularly scientifically valuable was that it was observed in extraordinary detail, because by 2019 the instrumentation available to astronomers had improved enormously compared to what was available even a decade earlier. The Atacama Large Millimeter Array in Chile, the Hubble Space Telescope, the Very Large Telescope in Chile, and multiple ground-based optical observatories all recorded the event across multiple wavelengths. The data set produced was unprecedented in its richness. Analysis of that dataset over the subsequent years has revealed several things about Betelgeuse's interior that were not previously known. First, the ejection originated from a single large convective cell near the southern hemisphere of the star's surface. And this convective cell produced a pressure wave that punched through the outer layers with enough force to eject material not just into the star's extended atmosphere, but entirely out of its gravitational hold, material that continues to travel outward to this day. The energy required to do this is enormous. The estimates of the total energy released in the ejection event run into figures that exceed the typical energy budget of a surface event on a red supergiant. Something in Betelgeuse's interior delivered an unusual amount of energy to that convective cell. Second, in the aftermath of the ejection, the affected surface region took far longer to return to its previous temperature than models predicted. The cooling of the dust cloud followed the expected pattern, but beneath the dust, the stellar surface itself remained anomalously cool for months, a scar that persisted through most of 2020. This persistent cooling suggested that the convective flow in that region had been disrupted at depth, not just at the surface. The plumbing of the star, in a sense, had been disturbed. Third, and most intriguingly, after the great dimming ended and the star's brightness recovered, Betelgeuse did something unexpected. It brightened significantly, more than normal. It became, for a period in 2023, one of the brightest stars in the sky, noticeably brighter than its long-term average. This brightening was itself unusual, and its interpretation is still being worked out. But one hypothesis that gained traction in the literature is that the surface mass ejection had, in some sense, temporarily disrupted the star's thermal equilibrium. The subsequent brightening represented a compensatory release of energy that had backed up in the interior while the surface was obscured. If that interpretation is correct, it tells you something important. The interior of Betelgeuse is generating energy in quantities sufficient to produce these dramatic surface effects. The energy budget of the star is not declining quietly towards some long, stable plateau before the final stages. It is active, turbulent, and variable in ways that are consistent with the more energetic burning stages. Put all of this together, the pulsation data, the character of the great dimming, the post-dimming brightening, the mass ejection energy budget, the neutrino detection prospects, and a picture emerges of a star that is not sitting comfortably in the middle of its red, supergiant phase, with thousands of centuries still ahead of it. The picture that emerges, at least in some of the most careful recent analyses, is of a star that is deep into its red supergiant phase, potentially in or approaching one of the final burning stages, with a timeline that the older models significantly underestimated. How did the older models get it so wrong? Or, to be precise, why might the older models have been incorrect? The honest answer is that they were correct, given the information available at the time, and the assumptions built into them were not unreasonable. The first detailed stellar evolution models for Betelgeuse were built in an era when direct imaging of the star's surface was not possible, when the pulsation record was shorter and less well characterized, and when the only available tools were theoretical stellar physics and the kind of inference from surface spectroscopy that can tell you a great deal but cannot penetrate to the interior. Those models took the measured luminosity of the star, its estimated mass, its temperature, and its evolutionary position, and asked, what internal state is consistent with all of these observations? The answer they got, helium burning, perhaps early carbon burning with a long remaining lifetime, was a defensible answer. It was not wrong. It was uncertain, and the uncertainty was acknowledged. What has changed is the data. The pulsation record is now much longer. The surface has been directly imaged in multiple wavelengths with resolutions that reveal the convective structure. The 2019 ejection event provided a deep diagnostic probe of the interior, and theoretical models of stellar oscillations have advanced to the point where the pulsation data can be used to constrain the interior structure with a precision that was not previously possible. When you update the older models with the new data, some of them produce revised timelines. Not all of them. The spread is still wide, but the direction of the revision in the analyses that take the full dataset seriously is consistently toward a shorter remaining lifetime, not longer. There is one additional piece of context that is worth spending some time on. or because it is frequently misunderstood in popular discussions of Betelgeuse's timeline. That is the question of what imminent means in stellar physics, and why the uncertainty in these estimates is not a reason to dismiss them, but is itself meaningful information. In everyday life, uncertainty is often treated as a reason to wait. If you're not sure whether it will rain, you might wait to see before deciding whether to bring an umbrella. This intuition doesn't translate well to astronomical timescales. When astrophysicists give a range of estimates, say somewhere between 100 years and 100,000 years, that range is not a schedule. It's an honest expression of the limits of inference. The event will happen at one specific time. Our uncertainty about when doesn't change the timing. It reflects our limited information about the star's current internal state. What the new data does is not so much move the expected value as dramatically narrow the range of plausible values. If the older models had a range of, say, 10,000 to 1 million years, and the new analyses are producing ranges of 100 to 10,000 years, that is a genuine scientific revision, even if the shorter end of both ranges is within a few centuries. The narrowing of the range is itself significant. It means the previously comfortable, not in any timescale that concerns us framing, is no longer obviously correct. It means, more precisely, that we can no longer confidently say that no human being alive today will live to see Betelgeuse explode. It's still unlikely. The most probable estimate, even in the more aggressive models, places the event beyond any current human lifetime. But unlikely is not impossible, and the window of time within which a human civilization, not ours specifically, but a recognizable human civilization on a recognizable Earth, might witness the event has shrunk dramatically. That shift in probability is not a curiosity. It is the kind of information that changes how you think about this object in the sky. It changes the emotional register of looking at Betelgeuse on a winter night. It changes what it means to know that the light entering your eye right now left that star in the 1300s, at roughly the same time the Black Death was sweeping through Europe. It changes the weight of the question, what will the world be like when the light that is leaving Betelgeuse tonight finally arrives? And it raises, for the first time in a scientifically meaningful way, the extraordinary possibility that sometime within the next several centuries, a human being, someone who will have language, memory, and the capacity for wonder, will look up at Orion on a winter night and watch a new sun appear. But there's more to the story of what's happening inside Betelgeuse right now, because the surface mass ejection and the pulsation shifts are not the only signals the star is sending. In the years since the Great Dimming, observatories have continued to monitor Betelgeuse with increasing frequency and precision, and the data they are accumulating is building toward a picture of a star in active, ongoing transition, not a static object sitting quietly in a known evolutionary state, but one that is visibly, immeasurably changing on timescales that astronomers can watch unfold. There is a moment in the life of a massive star that has no analogue in human experience. It is not a moment of violence, not yet. It is quieter than that, and in some ways more final. It is the moment when the nuclear burning in the core, the process that has sustained the star for millions of years, the outward pressure that has held gravity at bay across an almost incomprehensible span of time, begins to lose the argument. Not all at once, not suddenly. The losing happens in stages, each one faster than the last, each one bringing the core closer to the threshold, beyond which nothing can stop what comes next. And each of those stages leaves a signature in the light the star emits, in the way it pulses, in the neutrinos it bleeds into space, in the behavior of its surface, a signature that, if you know how to read it, tells you where you are in the countdown. We are now, for the first time in history, in a position to read those signatures in real time. Not perfectly, not without ambiguity, but with enough precision that the question, what stage is Betelgeuse in right now, is no longer purely theoretical. It is an observational question, one that real telescopes and real data are actively working to answer. Let's start with what those telescopes are currently seeing. Since the Great Dimming of 2019, Betelgeuse has been monitored more intensively than at any previous point in history. The American Association of Variable Star Observers, a network of mostly amateur astronomers who have been tracking Betelgeuse's brightness for over a century, continues to submit observations nightly. Professional observatories have added scheduled monitoring campaigns. The Atacama Large Millimeter Array, which can observe the star's radio emission and map its surface at millimeter wavelengths, has conducted repeated observations. The Very Large Telescope in Chile has produced direct images of the stellar surface in near-infrared light, and the James Webb Space Telescope, operational since 2022, has turned its instruments toward Betelgeuse with capabilities that represent a genuine leap beyond anything previously available. What this collective observation effort has revealed in the years since the Great Dimming is a star that has not returned to its pre-2019 behavior. It is not, as some hoped or assumed, back to a stable baseline. Its pulsation behavior remains altered. The 400-day dominant period appears shifted. The amplitude of the variations, how much the star brightens and dims over each cycle, has changed. And on top of all of this, the star has been exhibiting what astronomers are cautiously describing as increased surface activity, more frequent, more energetic outbursts of material from its convective surface. The James Webb Space Telescope observations deserve particular attention because they are producing data at a level of detail that is scientifically unprecedented for Betelgeuse. See, Webb's primary strength is infrared sensitivity, its ability to detect light at wavelengths longer than visible light in the thermal infrared, where the temperature structure of a stellar surface and its surrounding material can be mapped with extraordinary precision. For Betelgeuse, this means Webb can not only image the star's surface, but can trace the material ejected during and after the Great Dimming, the dust cloud that caused the dimming, and the subsequent material shed by the star's continued activity. What those observations have shown is that the dust cloud from the 2019 ejection is still present, still detectable, still moving outward through the space around the star. Its chemical composition has been analyzed in detail, and that composition is consistent with material from the outer layers of a red supergiant in an advanced evolutionary state, rich in oxygen and carbon compounds that form when the products of nuclear burning are dredged up from the interior and expelled through the stellar wind. The presence of these compounds in the ejected material is, in itself, a diagnostic of the star's internal chemistry. More significantly, Webb has detected what appear to be additional, smaller ejection events occurring after 2019. The star did not simply erupt once and settle back to quiescence. It has continued to shed material at an elevated rate compared to its pre-2019 behavior. The mass loss rate, The rate at which Betelgeuse is blowing itself into space appears to have increased since the Great Dimming, and that increase has not reversed. This matters for the timeline question in a specific and quantifiable way. As a red supergiant approaches the later stages of its nuclear burning sequence, its mass loss rate typically increases. The stellar winds grow stronger, the surface eruptions become more frequent, the star literally sheds more of itself per year as the internal energy output climbs during the more advanced burning stages. An elevated and increasing mass loss rate is, in the standard models of stellar evolution, one of the observable precursors to the final phases. It is not definitive. There are other explanations for elevated mass loss. The star may simply be in a phase of its normal long-period variation that happens to produce higher activity. The Great Dimming event itself may have temporarily disrupted the outer layers in ways that are still normalizing. These alternative explanations are not unreasonable, and any honest account of the current state of the science has to acknowledge them. But they are alternative explanations. They are the explanations you reach for when you want to avoid the more dramatic conclusion. And the weight of the accumulating evidence is making those alternative explanations increasingly strained. Let's now turn to the internal structure question, because understanding what is happening inside Betelgeuse right now requires understanding the onion model of a dying star. The layered structure that develops as each successive fuel source is exhausted. In its prime, Betelgeuse burned hydrogen uniformly throughout its core, a single, hot, centrally located fusion furnace. When that hydrogen was exhausted, the core contracted, heated up, and began burning helium. And the hydrogen that remained in a shell surrounding the now helium-burning core continued to fuse as well in what's called a hydrogen-burning shell. So the star went from having one burning region to having two, a helium-burning core and a hydrogen-burning shell around it. As the helium in the core was exhausted, the same process repeated. The core contracted again, heated further, and began burning carbon, while the surrounding helium-exhausted region became a helium-burning shell, and the outer hydrogen-burning shell continued above it. 3 burning regions now nested like layers of an onion. This onion layering continues through each successive burning stage: neon, oxygen, silicon. Each stage adds another layer. The core at the center burns the most advanced fuel, surrounding it in concentric shells. Earlier burning stages continue in a hierarchy of temperature and pressure. By the time a massive star like Betelgeuse reaches the silicon burning stage, it has developed a complex, multi-layered interior with a silicon burning core, oxygen, and neon burning shells outside it, carbon burning further out, helium burning beyond that, and hydrogen burning in the outermost shell. This layered structure is both the source of the star's extraordinary energy output in its final stages and the direct cause of the dramatic increase in neutrino emission. As the burning stages advance, the temperatures required to sustain fusion rise into ranges where a new process kicks in: thermal neutrino production. At the extreme temperatures of advanced burning stages, neutrinos are produced not just as a byproduct of specific fusion reactions, but as a result of the thermal state of the plasma itself, spontaneously, in enormous quantities. These neutrinos carry energy directly out of the star without interacting with the surrounding material, representing a massive energy loss that the star's remaining fusion processes must compensate for. This neutrino cooling becomes so significant during the oxygen and silicon burning stages that the star's remaining lifetime is measured not in years or decades, but in months and then days. The neutrinos are, in a real physical sense, draining the star of its remaining energy reserves at a rate that accelerates exponentially as the burning stage advances. For Earth-based neutrino detectors, this means the following. If Betelgeuse is in carbon burning, the neutrino flux from the star is elevated but still below current detection thresholds. If it advances to oxygen burning, the flux increases dramatically and should become detectable by next-generation instruments. If it reaches silicon burning, the flux becomes detectable even by current instruments, and there will be a window of days to weeks during which the detectors see an anomalous signal from the direction of Betelgeuse before the actual explosion occurs. This window, this neutrino precursor, is the closest thing to advance warning that science currently offers for a supernova event. The detection of such a precursor signal is one of the central scientific goals of the supernova early warning system. Junction Dome, or SNEWS, a network of neutrino detectors around the world that share data in real time specifically to provide early warning of a nearby supernova. SNEWS has been operational in various forms since the early 2000s. Its updated version, SNEWS 2.0, released in 2021, significantly improved its sensitivity and response time. If Betelgeuse progresses into the late burning stages, SNEWS and its member detectors, including Super Kamiokande in Japan, IceCube at the South Pole, and several others, will be among the first to know. The detection of a neutrino precursor from Betelgeuse would not mean the explosion was happening at that moment. Remember that the neutrinos travel at nearly the speed of light, while the light from the explosion follows the same path at the same speed. The neutrino burst from the core collapse itself will arrive at Earth a few hours before the visible light from the explosion, because the neutrinos escape from the collapsing core almost immediately, while the shock wave that produces the visible explosion takes hours to reach the star's surface. So the sequence of what Earth would detect in the final moments would be, first, a dramatic increase in neutrino flux over weeks or months from the advanced burning stages, then a sharp neutrino burst coinciding with core collapse, then a brightening of Betelgeuse's visible light hours later as the shock wave breaks through the surface. This sequence is not hypothetical. We observed almost exactly this sequence from supernova 1987A, the most recent naked-eye supernova, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, in February 1987. That event is the gold standard against which all models of core collapse supernovae are calibrated, and what it showed was that the neutrino precursor model was correct in its basic structure. The neutrinos from 1987A arrived at Earth's detectors hours before the visible brightening, exactly as predicted. Betelgeuse, at 700 light-years compared to the 160,000 light-years of 1987A, would produce a neutrino signal roughly 50,000 times more intense than what was detected from the 1987A event. It would be, without any question, the most significant neutrino detection in the history of physics. It would also be the most unambiguous possible confirmation that a supernova was hours away. Now, let's walk through the phases of what will actually happen, the sequence of events from the final burning stages through the explosion itself, because this is where the abstract physics becomes something visceral and concrete. Phase 1 is what we might be watching right now, the advanced burning phase. During this phase, which could last anywhere from centuries to decades depending on which burning stage Betelgeuse has reached, the star's behavior at its surface becomes increasingly chaotic. The energy output from the interior rises. The convection becomes more vigorous. Surface mass ejection events like the 2019 Great Dimming may become more frequent and more energetic. The stellar wind strengthens. The star may exhibit dramatic brightness variations, brighter periods followed by dimmer periods, as the surface responds to the fluctuating energy supply from below. From Earth, this phase looks like an increasingly active, increasingly variable star. Astronomers monitoring Betelgeuse will see the pulsation behavior continue to shift. The mass loss rate will continue to climb. If neutrino detectors become sensitive enough, they may begin to register a statistical excess in the direction of Orion. The star will not look catastrophically different to a casual observer. It will still be the familiar orange-red point of light in Orion's shoulder. But to instruments and trained observers, it will be broadcasting its distress in increasingly unmistakable terms. Phase 2 begins when silicon burning ignites in the core. At this point, though the remaining stellar lifetime is measured in days, the core is producing iron faster than any process can arrest the accumulation. The neutrino flux from the star spikes dramatically, not a gentle statistical excess, but a torrent of particles that modern detectors will catch unambiguously. Snooze triggers. Astronomers around the world receive automated alerts. The observation campaigns begin. Telescopes that can be pointed at Betelgeuse are pointed at Betelgeuse, and Betelgeuse on the sky still looks more or less the same, because the light we're seeing at that moment left the star 700 years ago. Whatever is happening inside the star right now, we won't see it for 7 centuries. The silicon burning, the iron core buildup, the final convulsions, all of that is happening in a version of Betelgeuse that exists 700 years in our past, and whose light is travelling toward us right now, carrying no information yet about what came after. This is one of the most conceptually strange aspects of observing a nearby supernova, and it's worth sitting with for a moment. The neutrinos, travelling at nearly the speed of light, will arrive at Earth slightly ahead of the light from the explosion, not because they're faster over cosmological distances, but because they escape from the stellar core before the photons from the exploding surface are generated. So we'll see the neutrino burst first, by a few hours, and then the light will arrive, and Betelgeuse, the star we've been looking at in Orion all our lives, will, over the course of a few hours, become something different. Phase 3 is the core collapse itself. It takes less than a second. The iron core, which has been accumulating over the days of silicon burning and which has grown to roughly the mass of the Sun, compressed into a sphere the size of a small city, reaches what's called the Chandrasekhar limit, the point at which electron degeneracy pressure can no longer support it against gravity. The collapse begins. In milliseconds, the core goes from roughly the size of Earth to roughly 20 kilometers in diameter. The density it reaches is nuclear density, the density of an atomic nucleus, the densest form of matter that can exist without becoming a black hole. The collapse halts abruptly at this density because at nuclear density, the strong nuclear force becomes repulsive, creating a hard floor that the infalling material bounces off. That bounce generates the shock wave. A pressure wave of almost unimaginable intensity propagates outward through the star's interior, moving through the onion layers, gaining energy as it goes, or, more accurately, losing energy to the surrounding material, but being re-energized by the continuing flood of neutrinos from the newly formed neutron star at the center. The mechanism by which the neutrinos re-energize the stalled shockwave is one of the most intensely studied problems in computational astrophysics, and the details are still not fully resolved. But the outcome is the shockwave wins. It pushes through the outer layers. It accelerates as it approaches the star's surface, which is, remember, hundreds of solar radii away from the core where all of this started. Phase 4 is the shock breakout. After hours of travel through the star's interior, the shockwave reaches the surface. This produces what is, in some ways, the most spectacular moment of the entire event, the first burst of visible and ultraviolet light that signals to the universe that this star has exploded. The shock breakout is brief, lasting minutes to hours, but it is enormously luminous, briefly outshining even the subsequent supernova peak. For an observer on Earth, this would be the moment when Betelgeuse suddenly flares to extraordinary brightness with almost no warning in the visible light. One moment, a familiar orange star. Minutes later, something that hurts to look at directly. This is the moment that will be seen from Earth 700 years after it happens inside the star. The moment that will change the sky. And from there, the expansion of the explosion proceeds over days and weeks, the ejector expanding outward at a significant fraction of the speed of light, the brightness climbing to its peak over several days, the light output at peak being comparable to the entire rest of the galaxy combined, and then slowly, over weeks and months, fading as the expanding cloud of stellar debris thins and cools. What remains at the center, after all the outer layers have been flung into space, depends on the final mass of Betelgeuse's core. If the core ends up below roughly 3 solar masses, it will settle into a neutron star, a city-sized sphere of nuclear density matter spinning at potentially hundreds of rotations per second, radiating beams of radio waves as a pulsar. If the core mass is above this threshold, not even the strong nuclear force can hold it against gravity, and it continues to collapse into a black hole. Current estimates of Betelgeuse's mass suggest the neutron star outcome is more likely, but the uncertainty in the mass estimates is large enough that the black hole outcome cannot be ruled out. Either way, the star that we see tonight in Orion's shoulder will be gone. In its place, if the timing is right, and if whoever is alive on Earth thousands of years from now is lucky, there will be a nebula, a glowing cloud of gas and dust, expanding slowly into the space around it, lit from within by the compact remnant at its center, the same raw material from which planets form, the same elements from which life is built, carbon, oxygen, nitrogen, iron, all the things that stars cook in their cores and then, in dying, is give back to the universe. That is the full sequence. That is what is coming. The question that the new data is forcing us to reckon with, the question that makes this more than academic, is where exactly in that sequence Betelgeuse currently sits. Not 100 years before Phase 1, as the old estimates suggested, but possibly within Phase 1 already, possibly closer to Phase 2 than any previous model predicted. Imagine you are standing outside on a clear winter night, sometime in the next few centuries. The exact year doesn't matter. What matters is the sky above you, the same sky that has looked essentially the same to every human being who has ever lived, the same arrangement of stars that guided sailors and inspired myths and gave ancient civilizations their calendars and their gods. Orion is up, as it always is in winter, with the familiar silhouette of the hunter standing against the dark. The 3 belt stars, the sword, the raised arm. And there, at the shoulder, the reddish-orange point of light that has always been there, that every person who has ever looked at that constellation has seen, that has burned in that position for the entire span of human history and long before. And then something changes, not slowly, not over weeks or years, building so gradually that you might miss it if you weren't watching carefully. Suddenly, in the span of hours, maybe less, the point of light at Orion's shoulder begins to brighten. Not the gentle brightening of a planet rising or a star coming into better atmospheric conditions, a brightening that is wrong in the way that only truly unprecedented things are wrong, a brightening that your eyes register as something requiring explanation before your brain has consciously formed the question. By the next night, it is unambiguous. Betelgeuse is no longer a point of reddish light. It is the brightest object in the night sky by an enormous margin. Brighter than Venus at its most brilliant, brighter than Jupiter, brighter than anything that has appeared in the sky since the last time something like this happened, which, for a star this close, has never happened in recorded human history. The star casts shadows, faint ones at first, but real. You can hold up your hand and see the shadow of your fingers on the ground cast by starlight, by a single star. Within days, it gets brighter still. At peak brightness, which most models predict will arrive 3 to 5 days after the initial shock breakout reaches the star's surface, Betelgeuse will shine at an apparent magnitude somewhere between -6 and -10. To give that number meaning, Venus, the brightest planet, reaches about magnitude -5 at its most brilliant. The full moon sits at magnitude -13. Peak Betelgeuse will fall somewhere between Venus and the full moon in terms of raw brightness, likely closer to the moon end of that range. It will be, without any historical precedent in the modern era, the brightest star event any living human has ever seen. And it will be visible in daylight, not easily. Not the way the sun and moon are visible during the day. You won't be able to just glance up and find it casually. But if you know where to look, if you shield your eyes from the sun and find Orion's approximate position in the sky, you will be able to see a point of light that should not be there. A star, visible at noon. The last time something like that was reliably reported happened in 1006 AD, when a supernova in the constellation Lupus, now known as SN 1006, briefly achieved roughly similar brightness levels and was recorded by astronomers in China, Japan, Egypt, Iraq, Switzerland, and across the Islamic world as a star visible during the day. That event happened at a distance of roughly 7,000 light-years. Betelgeuse is 10 times closer. The daytime visibility will last for weeks, perhaps as long as a month, depending on the exact brightness curve of the explosion and how quickly the expanding debris cloud begins to thin. During this period, the sun will set in the west, and Betelgeuse will set perhaps 2 hours later, still blazing. There will be a period of roughly an hour or two each night when both have set and the sky achieves something close to full darkness. And then Betelgeuse will rise again in the east, before the sun, burning through the pre-dawn sky. For the months during which Betelgeuse remains brighter than any star in the sky, which could last anywhere from 3 months to a year. Depending on the nature of the explosion, the night sky will be fundamentally different from anything that has existed during the entire span of human civilization. The Milky Way will still be there on dark nights away from city lights, but it will be competing with a new light source. The familiar seasonal patterns of stars will still hold, but embedded in Orion, right at the hunter's shoulder, will be something that doesn't belong, something that glows with a blue-white intensity, rather than the familiar orange of the star that was there before, because the explosion's light will be bluer and hotter than the red supergiant surface it replaced. Orion as a constellation will be permanently changed. After the supernova fades, after months or years, when the debris cloud has expanded and thinned enough that the naked eye can no longer detect it, what will remain will not be a star. It will be, for decades or centuries, a glowing nebula, a soft smear of light visible through binoculars and eventually only through telescopes, expanding slowly outward, cooling and fading over centuries. And where Betelgeuse once anchored the hunter's shoulder with a bright reddish point, there will be nothing visible to the unaided eye, a gap in the constellation, an absence where something ancient used to be. Every culture that has ever given meaning to Orion, and there are dozens of them across every continent in every era of recorded history, will have to reckon with that absence, the hunter's shoulder gone. The pattern that navigators used to find direction, that farmers used to mark the seasons, that storytellers used to anchor their myths of winter and the sky, permanently altered. This is not hyperbole. It is the straightforward consequence of the brightest star in one of the most recognizable constellations in the sky ceasing to exist. Let's sit with what that means, not just scientifically, but in the fullest sense of what it means for human beings to exist on a planet where this is happening. Every single person who has ever lived on Earth has seen Orion with Betelgeuse in it. Every person who will be alive when the light from the explosion arrives will spend the rest of their lives knowing that the sky they see is not the sky that their ancestors saw. Something fundamental about the visual landscape of human existence, a constant that has persisted for longer than our species, will have changed. Not because of anything humans did, not because of war or climate or any of the 1,000 ways we change our own world, but because the universe, on its own schedule and by its own processes, reached the end of a countdown that began 8 million years ago. There is something about this that resists full comprehension in the way that most large facts do not. We are accustomed in the modern world to change. We are accustomed to landscapes being altered, technologies replacing each other, buildings rising and falling. We are accustomed even to species going extinct and ecosystems shifting. But the sky is the one thing that has remained constant across all of that change, the one reference point that has connected every human generation to every other, a shared visual anchor that exists above and beyond the reach of anything we do. When the sky changes, when a star that has been there since before our species existed simply vanishes, something changes in the relationship between humanity and the cosmos that is genuinely without precedent. The cultures that will witness this event will not be our culture. They will speak languages we might not recognize. They will have technologies we can't anticipate. They may have spread beyond Earth, or they may still be living here, but they will be separated from us by centuries of history that we will never know. And yet, they will share something with us, with everyone alive today, with everyone who has ever looked up at Orion on a winter night, because they will have spent their lives under a sky with Betelgeuse in it, just as we have. And then one night or one morning that sky will change, and they will carry that change for the rest of their lives, and tell the story of it to their children. And their children will grow up in a world where Betelgeuse is a story rather than a star. That moment, the moment of witnessing, is worth thinking about in more detail because it raises questions that are not purely scientific and not purely philosophical, but somewhere in between. And consider what it means to actually observe the death of a star, not metaphorically, not through data, but with your eyes. The light that arrives on Earth when Betelgeuse explodes will have travelled for 700 years. It will have left the star during a period of human history that we know in broad strokes but not in detail. A world without electricity or telescopes or any of the tools that make modern astronomy possible. That light will carry the information of the explosion encoded in its spectrum, the temperature of the ejector, the chemical composition of the debris cloud, the energy of the shock wave. It will be, for astronomers, an extraordinary data set. But for anyone standing outside looking up, it will be something simpler and stranger than data. It will be a death, arriving after 700 years in transit. The star will already be gone. By the time the light reaches us, Betelgeuse, as a red supergiant, as the thing that has been burning in Orion's shoulder for all of human history, will have ceased to exist 7 centuries earlier. What we will be watching when the explosion lights up our sky is not something happening now. It is a record of something that happened long ago, finally arriving at the one small place in the galaxy where creatures exist who can understand what they're seeing and feel something about it. This is true of all starlight, of course. Everything we see when we look at the night sky is the past. Some of it the recent past, some of it the ancient past. The star Proxima Centauri, the closest star to the Sun, appears to us as it was 4 years ago. The stars of Orion's belt appear to us as they were 600 to 1,300 years ago. The Andromeda Galaxy appears to us as it was 2.5 million years ago. We are always looking at history when we look at the sky. The sky is a time machine that only moves in one direction. But there is something different about watching an explosion, about watching a specific event rather than a steady state. When you look at Betelgeuse right now and see an orange point of light, you are seeing the star as it was in the 1300s, burning steadily, doing nothing dramatic. But somewhere in the 700 light years of space between us and where Betelgeuse sits, the light from every subsequent moment of that star's history is travelling toward us. The light from its dimming in 2019, the real 2019, the actual event at the star, will not arrive here until roughly the year 2079. The light from whatever is happening inside Betelgeuse right now will not arrive for another 700 years. And somewhere in that stream of light travelling toward us, somewhere in the centuries of photons currently en route, there may be the light of an explosion, already travelling, already in transit, already carrying its 700-year-old message toward a planet that doesn't know yet what's coming. The idea that the light of Betelgeuse's death might already be on its way to us, that the explosion might have already happened in the objective physical sense that the event has already occurred and we simply haven't received the information yet, is one of those ideas that sounds like science fiction, but is straightforwardly, literally true. It is not a metaphor. The light travels at a finite speed. The event, if it has occurred centuries ago. We are waiting, without knowing we are waiting, for a message that may already be in transit. This is the version of the Betelgeuse story that doesn't get told often enough. Not, will it explode? We know it will, but has it already exploded? And the honest answer is, we don't know. We cannot know. The physics of light speed means that for any star within a few thousand light years, the question of whether it has already exploded is genuinely open and genuinely unanswerable with current technology. The star we see is the star as it was centuries ago. The star as it is right now is invisible to us because right now's light hasn't arrived yet. What the new data tells us is that the probability of the explosion having already occurred is non-trivial, not certain, not even likely, and in the strict probabilistic sense, but no longer negligible. If the revised timeline is correct, if the remaining lifetime of Betelgeuse is measured in centuries rather than tens of thousands of years, then there is a real, calculable probability that the explosion has already happened and that the light from it is already en route. The universe may have already sent the message, we are just waiting for it to arrive. Now, let's talk about what the explosion will mean for Earth in practical terms, because this is a question that always arises, and it deserves a careful, complete answer rather than a dismissive, "Don't worry, we're safe," or an irresponsible, "It could be catastrophic." The answer, in its most precise form, is this. Betelgeuse is far enough away that the explosion will not endanger complex life on Earth. The estimates of the lethal distance for a supernova, the distance within which the radiation and high-energy particle flux would be sufficient to cause significant ozone layer damage and biosphere disruption, generally range from 25 to 50 light-years in the most conservative analyses. Some recent papers have pushed that estimate as high as 100 light-years for the most severe potential effects. Betelgeuse is 700 light-years away. It is comfortably outside the danger zone by any current estimate. What Earth will actually receive from the explosion is significant in scale, but not in terms of biological threat. The gamma-ray flux arriving at Earth will be roughly equivalent to a few minutes of normal solar ultraviolet exposure at the surface level. Noticeable in terms of detector sensitivity, it's but not remotely close to levels that affect human health. The increase in cosmic ray flux, high-energy particles from the supernova remnant, will be real, but will arrive gradually over years and centuries as the remnant expands, and will represent a modest increase above background levels rather than a sudden dangerous spike. The most significant physical effect on Earth from the explosion will be the light itself, and, specifically, the disruption of the day-night cycle on a small but real scale. During peak brightness, Betelgeuse will contribute enough light at night to affect some light-sensitive biological processes. Animals that navigate by darkness, certain nocturnal species, migratory birds that use star patterns for orientation, coral reef systems that spawn based on lunar light levels may experience measurable disruption during the months when the supernova is at or near peak brightness. These effects will be temporary, fading as the explosion dims, and are unlikely to cause long-term ecological damage, but they will be real. For human civilization, the effects will be almost entirely psychological and cultural rather than physical. The explosion will be visible. It will be impossible to ignore. It will demand explanation and response from every society on Earth at the time. And the explanation for any civilization that has maintained astronomical knowledge will be profound in a way that resists easy summary. Because knowing what you are seeing, knowing that you are watching a star 700 light-years away tear itself apart, lest knowing that the light entering your eyes left that star 7 centuries before you were born, knowing that in the debris cloud expanding outward from the explosion are the heavy elements that will eventually form new planets and new solar systems and potentially new life, changes the experience of watching it. It makes it not just a spectacle, but a meditation, a confrontation with the scale and the age and the absolute indifference of the universe, presented in the most visceral possible format, a light in the sky that you cannot explain away and cannot stop watching. The ancient astronomers who recorded SN 1006, the last supernova of comparable brightness, did not know what they were seeing. They called it a new star. They interpreted it as an omen, a sign, a message from the heavens that meant something about human affairs. And they were not wrong to feel that it meant something. They were simply working with a vocabulary that didn't yet include the words core collapse or neutron star or nuclear fusion. They had the response right. They just didn't have the explanation. We will have the explanation. And the question is whether the explanation makes it more meaningful or less. Whether knowing the physics of what you're watching adds something to the experience of watching it, or strips away the mystery that made it feel significant. The answer, for most people who think about this seriously, is that the physics adds to it, rather than subtracting. That knowing a star lived for 8 million years and burned through successive layers of nuclear fuel until the iron in its core finally shut off the last possible reaction, and then collapsed in a single second and bounced and exploded, knowing that the light you're seeing is 8 million-year-old nuclear physics finally arriving at its conclusion, makes the experience larger, not smaller. It connects the point of light in the sky to a story that is genuinely as vast as the universe, and it connects you, standing there in the dark, looking up, to that story in a way that is real and not metaphorical. You are, after all, made of elements that were produced in exactly this process. The calcium in your bones, the iron in your blood, the oxygen in the air you're breathing right now, all of it forged in stars that exploded before the sun existed, seeding the gas cloud that eventually collapsed to form our solar system. You are, in the most literal possible sense, the product of previous Betelgeuses, previous red supergiants that burned through their fuel and exploded and scattered their contents into the interstellar medium, and whose debris eventually became you. Watching Betelgeuse explode will not be watching something foreign happen at a safe distance. It will be watching the process that made you running one more time, making something new. That is the experience waiting for whoever is alive when the light arrives. That is what the revised timeline, the new data, the shortened countdown means when translated into human terms. Not danger, not crisis, but the extraordinary, unprecedented, once-in-a-civilization opportunity to witness one of the universe's most fundamental processes with the naked eye. And the fact that we might be closer to that moment than anyone previously thought, that the people who will see it might be our descendants rather than strangers separated from us by geological time, is not a source of anxiety. It is a gift from a dying star that has been burning since long before our species existed, and that will, in its final act, light up our descendants' sky in a way that none of them will ever forget. There is a particular kind of knowledge that sits differently from other kinds, not the knowledge that changes what you do, or the knowledge that solves a problem, or the knowledge that gives you an advantage over uncertainty. A different kind, the kind that simply changes how you see. The kind that, once you have it, makes the world slightly different from what it was before, not because the world has changed, but because you have. Knowing what Betelgeuse is and what it is doing, and what the new data suggests about when it will finish doing it, is that kind of knowledge. It doesn't protect you from anything. It doesn't give you a practical advantage. It doesn't change your morning or your evening or any of the immediate texture of your life. But it changes the winter sky. It changes what you see when you find Orion, when your eyes settle on that reddish-orange point of light at the hunter's shoulder. It makes that point of light heavy with something that wasn't there before you knew. a weight of time and imminence, and the particular melancholy of watching something beautiful that is also ending. We've covered the physics, we've covered the data, we've covered the debate and the timeline and the sequence of events from advanced burning to core collapse to the light arriving at Earth. Now, in this final part, we're going to close the loop, to bring together everything we've discussed into a coherent picture of where we are, what the coming decades will reveal, and what the legacy of this moment in the story of Betelgeuse actually means. Let's start with a summary of the timeline as it currently stands, not the old estimate, but the full range of current scientific opinion, presented honestly. The pre-2019 consensus placed Betelgeuse in the helium-burning phase, with a remaining lifetime estimated at somewhere between 10,000 and 100,000 years. That estimate was not invented. It was the output of reasonable models applied to the best available data, and it reflected genuine scientific thinking rather than guesswork. Its wide range acknowledged the genuine uncertainties in Betelgeuse's mass, internal structure, and evolutionary state. The post-2019 picture is different in several important ways. The pulsation analyses, particularly the work examining whether Betelgeuse's oscillation modes are consistent with carbon burning rather than helium burning, have produced estimates that some researchers are now placing at between a few hundred and a few thousand years. The most aggressive interpretations of the data push the lower bound below 100 years. The most conservative interpretations maintain that the available evidence is insufficient to distinguish between the new scenario and the older timeline with confidence. The debate is real, ongoing, and not resolved. What can be said with genuine confidence is this: the range of scientifically defensible estimates for Betelgeuse's remaining lifetime has shifted dramatically downward compared to where it sat a decade ago. The comfortable buffer of tens of thousands of years can no longer be assumed. The new data does not prove a short timeline, but it has made a short timeline a legitimate possibility rather than an outlandish one. And that shift in the bounds of scientific opinion is itself significant. The question now is not, will the estimate keep shifting? It will. The question is in which direction and by how much, and that question will be answered, partially, gradually, imperfectly, by the observations of the coming years and decades. Because we are entering what may be the most scientifically productive period in the history of Betelgeuse observation, and the instruments that are coming online now and in the near future will provide data that previous generations of astronomers could only dream of. The James Webb Space Telescope, already operational, will continue to produce infrared observations of Betelgeuse's surface and surrounding material at unprecedented sensitivity. Its ability to trace the chemical composition of the material the star is shedding, to look for the signatures of advanced nuclear-burning products being dredged up to the surface and expelled in the stellar wind, will provide direct evidence of the star's internal chemistry over the coming years. If Betelgeuse is in the carbon-burning phase, the Webb should be able to detect the chemical signatures consistent with that stage in the composition of its outflowing material. The extremely large telescope, the ELT, currently under construction in the Atacama Desert in Chile, with a primary mirror 39 meters in diameter, will, when it achieves first light in the late 2020s, be capable of resolving Betelgeuse's surface in visible light, with a resolution that makes current imaging look blurry by comparison. The convective cells, the surface temperature variations, the pattern of mass ejection, all of it will be visible in detail that will allow direct comparison with the predictions of stellar evolution models. The ELT will not just observe Betelgeuse, it will effectively give us a real-time view of the processes that are determining the star's fate. Hyper Kamiokande in Japan, the next-generation neutrino detector that represents a major upgrade over its predecessor Super Kamiokande, is scheduled to begin operations in the mid to late 2020s. Its sensitivity to low-energy neutrinos is sufficient that if Betelgeuse is in the carbon-burning phase, there is a realistic possibility of detecting a statistical excess of neutrinos from the direction of Orion. Not the dramatic burst of a core collapse, but the quieter, sustained elevation of neutrino flux that accompanies advanced burning. This would be, if it occurs, the first time in history that the internal nuclear processes of a star other than the Sun have been directly detected through neutrino observation. It would be, without any overstatement, one of the most significant observational results in the history of astrophysics. And then there is the gravitational wave frontier. The core collapse of a massive star is expected to produce gravitational waves, ripples in space-time generated by the asymmetric, violent redistribution of enormous mass in milliseconds. Current gravitational wave detectors, LIGO and Virgo, are sensitive enough to detect the gravitational wave signal from a core collapse supernova within the Milky Way, though the signal would be weak and require careful analysis to extract from background noise. Next-generation detectors, including the proposed Einstein telescope in Europe and Cosmic Explorer in the United States, will be dramatically more sensitive. If Betelgeuse collapses within the operational lifetime of these instruments, which, depending on the timeline, is not an unreasonable prospect, the gravitational wave signal from the collapse will be detected, providing a simultaneous multi-messenger observation of the event alongside the neutrino burst and the electromagnetic signal. A multi-messenger observation of Betelgeuse's core collapse, neutrinos, gravitational waves, and light, all arriving within hours of each other, all carrying independent information about the same cataclysmic event, would be the most information-rich astronomical observation ever made. It would test the core collapse supernova models against reality with a completeness and precision that no previous event has permitted. It would answer questions about neutron star formation, neutrino physics, and the mechanics of the shockwave reheating process that have remained open for decades. It would be a scientific windfall of extraordinary proportions. This is the scientific inheritance waiting for whoever is alive and watching when Betelgeuse finally goes. Not just a spectacle in the sky, but a data set of incomparable richness, a natural experiment that the universe has been preparing for 8 million years and that will run for hours, days, and weeks, observed simultaneously by every instrument humanity has ever built that is capable of seeing it. But before we arrive at that moment, there is the question of what the coming decades of monitoring will tell us, not just about the timeline, but about our ability to predict stellar death in general. Betelgeuse is, in a very real sense, a test case. It is the nearest massive star that we know is approaching the end of its life. It is close enough to observe in extraordinary detail across multiple wavelengths, with instruments that can resolve its surface and probe its interior through pulsations and neutrinos. If we can use all of these tools to correctly identify where Betelgeuse sits in its evolutionary sequence, if we can, over the coming decades, narrow the range of timeline estimates to the point where we can say with genuine confidence that the explosion is or isn't within a particular window, then we will have demonstrated an ability to monitor and predict stellar death that can be applied to every other massive star in the galaxy. The implications of that capability extend well beyond Betelgeuse. There are hundreds of massive stars in the Milky Way that will eventually explode as supernovae. Most of them are far enough away that they pose no threat, and their explosions will be observed as distant events rather than local spectacles. But some of them are close enough that advance warning of their imminent explosion would be scientifically invaluable, allowing observatories to be pointed at the right place at the right time, ensuring that when the next nearby supernova occurs, it is observed from the very first moments, rather than detected after the fact. The story of SN 1987A is instructive here. When that star exploded in the Large Magellanic Cloud in February 1987, the neutrino burst was detected by existing detectors, but barely, and with only a handful of events. The visible explosion was first noticed by a Canadian astronomer, Ian Shelton, who was checking a photographic plate of the Magellanic Cloud and realized that a star had appeared where none had been before. The detection was serendipitous. The scientific value of the observation was enormous, but it was limited by the fact that nobody was specifically watching that star in the moments before and during the explosion. For Betelgeuse, the situation will be completely different when Betelgeuse explodes, whether in 100 years or 1,000. It will be the most anticipated astronomical event in history. Every detector that can be pointed at it will be pointed at it. Every observatory in every wavelength will have protocols ready. The neutrino detectors will have been designed specifically with this event in mind. The gravitational wave detectors will be listening, and the light, when it arrives, will be captured not just by professional instruments but by every amateur astronomer with a camera on every clear night in every part of the world. The death of Betelgeuse will be the most watched event in the history of astronomy, and the data it produces will rewrite textbooks. Now let's widen the lens one final time and ask the deepest version of the question that this entire video has been circling. What does it mean that we know this? What does it mean to live in the first era of human history in which we can look at a dying star and understand, in genuine scientific detail, what is happening inside it and what is coming? For most of human history, the stars were eternal. Not metaphorically eternal, actually eternal, in the sense that nobody expected them to change. Like the word planet, in ancient Greek literally means wanderer, a name given to the objects that moved against the fixed background of the stars, because the stars themselves didn't move. They were the fixed things, the permanent things, the backdrop against which the changing world played out. The idea that stars were themselves subject to change, that they could be born and age and die, is a modern insight, barely a century old in its full form. We are the first humans to look at Betelgeuse and know that it is dying. Every person who ever looked at that star before the modern era saw something they believed was permanent. We see something we know is temporary. We see a fire that has been burning for 8 million years and is running out of fuel, and we can estimate, imperfectly, with wide error bars, but genuinely, how much fuel is left. That knowledge is strange and heavy in a way that's difficult to articulate. It connects the abstract machinery of astrophysics, the nuclear burning sequences, the pulsation modes, the neutrino fluxes, to the most immediate possible human experience, which is lying on your back on a winter night, looking at a point of light and understanding, in some cellular way, that you are small and the universe is large and the universe does not stop for anything. But there is another side to this knowledge that is less heavy and more remarkable, and it deserves to be stated clearly. We figured this out. We, this small, briefly living species on a pale blue dot, orbiting an unremarkable star in the outer arm of an ordinary spiral galaxy, figured out that the reddish-orange light in Orion's shoulder is not a fixed point, but a dying star. We figured out how stars work, how they burn, how they die. We built instruments sensitive enough to count individual neutrinos arriving from nuclear reactions happening in stellar cores. We built telescopes that can resolve the surface of a star 700 light-years away, that can see individual convective cells on a surface so distant that the light takes 7 centuries to reach us. We built mathematical models of nuclear physics and fluid dynamics and general relativity that, together, describe the evolution of a star from gas cloud to neutron star with an accuracy that makes predictions we can test. None of that was given to us. All of it was worked out slowly and collaboratively over generations by people who asked questions and then refused to be satisfied with incomplete answers. The history of how we came to know what we know about Betelgeuse is itself a remarkable story, a story of spectroscopy developed in the 19th century, of stellar evolution theory built in the 20th, of neutrino physics born in underground laboratories, of interferometry that can measure angles smaller than anything the human eye can resolve, all converging on this one reddish point of light in a winter constellation. We live right now at the moment in that long story where the tools have finally become good enough to ask the question, how long until, and receive an answer that is genuinely constraining rather than purely speculative. Are the new data from Webb, from the pulsation analyses, from the mass ejection observations, all of it represents the current state of that long collaborative project. It is not the final word. It will be refined and revised and perhaps overturned. But it represents the best answer our civilization has ever been able to give to the question of when Betelgeuse will die. And that answer, uncertain, contested, but genuinely narrowed, is sooner than we thought. Let's close with the countdown itself. Not the technical version, the carbon-burning phases and the silicon-burning days and the neutrino precursor signals, but the human version, the version that sits in the body rather than the mind. Somewhere between now and a few thousand years from now, most likely in the earlier part of that range. If the new analyses are correct, a star 700 light-years away will undergo core collapse. In less than a second, a stellar core the mass of the Sun will compress to the size of a city. The shockwave will propagate outward through the star's layers for hours. The surface will explode. And light, an almost incomprehensible quantity of light, will begin traveling outward in all directions at 300,000 kilometers per second. 700 years later, that light will reach a small planet orbiting a yellow star in the outer arm of the Milky Way. And, on that planet, if there are creatures capable of looking up, creatures with eyes and curiosity and the capacity to wonder, they will see something new in the sky. Something that wasn't there yesterday. A light at the shoulder of a familiar constellation, burning with an intensity that makes the stars around it look like embers. They will not know in that first moment what they are seeing. Even if they have all of our knowledge and more, there will be a moment, the moment of first seeing, before explanation, before analysis, before the instruments are checked and the models are consulted. A pure moment of confrontation with something unprecedented, a moment in which a human being looks at the sky and understands, wordlessly and completely, that the universe has just done something that cannot be undone. That moment is waiting somewhere in the future. The light that will create it may already be in transit, already crossing the void between Orion and Earth, carrying its 7-century-old message toward a planet that doesn't know yet that it's coming. Or the light may not yet have departed. The explosion may still be ahead, still waiting for the iron core to reach its limit, still subject to the ticking of a clock that our instruments are only now learning to read. We don't know which. We cannot know which. The speed of light is the speed of light, and the universe does not send previews. What we know is that it is coming, that the star burning in Orion's shoulder tonight, the star that every human being who has ever lived has seen, that guided sailors and inspired myths and anchored constellations across the full span of recorded history, is in its final chapter. Not its final sentence, perhaps, not its final paragraph, but its final chapter. And we are, for the first time, close enough to the end of that chapter to feel it. Not in any practical or physical sense, not in any way that changes tomorrow's weather or next year's harvest or anything about the immediate texture of human life, but in the way that knowing changes things. In the way that looking at a familiar point of light and understanding what it is and what it is becoming and what it will do to the sky when it finally lets go. In that way, in the quiet weight of that knowledge, we are closer to the end of Betelgeuse's story than any generation before us has ever been. Go outside tonight if it's winter, if Orion is up. Find the belt, look up and left. Find the reddish-orange point of light at the shoulder. Look at it for a moment. Really look. Not a glance, but a real, sustained look of the kind that is becoming rare. That light left the star around the year 1325. And the Battle of Bannockburn had just been fought in Scotland. The Ottoman Empire was in its first decade. The Black Death had not yet reached Europe. Dante was alive and working on the Divine Comedy. The world that sent you this light was not the world you live in, and the person who will one day see the light that is leaving Betelgeuse tonight has not yet been born, and will not be born for centuries. You are standing in the middle of that story, looking back 700 years at one end, looking forward 700 years at the other. And in the present tense, and in the star as it actually is right now, in whatever nuclear fires are currently burning or failing to burn in a core 700 light years away, the countdown is running. We just don't know the number. The new data says it's smaller than we thought. Watch the sky.